begin with a couple of comments. One, Professor Mani just told me that formula which I was calling the Parseval formula is actually called the also called the Plancherel formula, and there is a relatively easy way in which to extract the completeness relation that we were talking about yesterday without having to go to that Plancherel formula and sort of tear it apart. It is one thing I wanted to tell you. Another is an amusing thing. There's a very talented young girl here who is a student in the mathematics department. Mathematics, what do you call, division, or whatever it is. And she told me at breakfast or lunch or dinner yesterday that I was attending one of your lectures and I could see how differently physicists and mathematicians approach the same subject, and you were talking about groups and so many parameterizations all the time. So I had to tell her, look, we have to learn to do practical calculations, and for that purpose it is necessary to be familiar with these things. And then today when I was looking over my notes, I was reminded of a very nice sentence from Feynman's lectures on gravitation. I don't know how many of you have seen, that, I think. There he says that everything is coordinate independent, but when you want to prove something or check something, you may find it most convenient to use a suitable coordinate system to do the calculation. And the nice phrase in his account is, there need be no sense of defeat in using a coordinate system. So I like that sentence very much, which means that you know fully well whatever you are doing has an invariant meaning, and it is not out of fear that you decide to check something using some coordinate system. Who would want to solve the hydrogen atom Schrödinger equation in Cartesian coordinates? So
somebody asks you whether you visit somebody and the lady asks whether you want coffee, tea, or fresh lime.
Yeah.
Say everything, then the problem doesn't get solved. You just actually choose a body.
Yeah, that is true. Yeah. So this is just a light-hearted comment that it is true that with our background and training, we need to see things in somewhat more explicit, down-to-earth form before we feel comfortable. And those with a more rigorous mathematical training and aptitude, they can dispense with some of these things. Okay? So I just wanted to mention that. So I want to continue the discussion of the group SU2 and its properties, and I want to look at few uses of the axis angle description. It is convenient for two or three things. The way we have set it up is this correct? Something is wrong. By alpha, right? This is correct. Now, if you take a 3-vector alpha with a very small magnitude and you calculate up to quadratic terms, you can use the power series expansions for the cosine and the sine, and you will find that up to quadratic terms you get this, and then cubic and so on. Of course, this term is multiplied by the unit matrix, that is understood. Now, one of the ways in which we can, one of the things for which we can use this axis angle description is to see very easily how group multiplication appears for elements near the identity. I will do that first, then we will look at some topological properties, and then come to the classes conjugation operation. So now suppose you take two elements, u of alpha, u of beta, and you imagine both alpha and beta. Yeah. Here. Yes, yes, there is a 2.
But will you get it?
Oh, I'm sorry. Let me just see. I have forgotten now. How was it? Maybe there's no 2 there. It is in sine alpha, but I'm sorry. There is no 2 here. There is no 2. It is there in the sine. So you're right. Minus I. Now you take 2 elements close to the unit element, identity element, I'll say parameters alpha and beta, and then you ask what is the group composition law. Now let us tentatively write this as alpha plus beta plus some gamma, and we want to know what does gamma look like. So what we will do, see, we expect gamma to start off with terms of the type alpha times beta and then higher order terms. So as we did once before, let us calculate retaining only terms linear in alpha, linear in beta, and in second order only cross terms. That is, we ignore alpha squared and beta squared. So for the 2 factors on the left, it is enough to write only this much. I can ignore the alpha squared over 8 and alpha beta squared over 8. So in the same way, on the right, what will I get? Now, to my stated degree of accuracy, should I stop here or should I go to this quadratic third term on the right hand side? What do you think? Should I or should I not go? I should, because I want to retain terms of the cross between alpha and beta, and in there will be such a contribution in minus 1 by 8 alpha plus beta plus gamma whole squared. In that expression I can forget gamma, and the only term I will get involving 2 alpha dot beta. Right? So you have to be consistent, retain exactly the terms that you are shooting for. Correct? Plus there will be other terms, doesn't matter. Now compute the left hand side and compute the right hand side. 1 times 1 will go with this one. These things will go with the cross terms. The surviving term, what is there on the left hand side? It is minus 1 by 4 alpha dot sigma into beta dot sigma. How much is that? Alpha dot beta plus I alpha, yes, sigma. Is there a half or anything? Just check. Is it I by 2? Alpha dot sigma into beta dot sigma. Is there a I by 2 in the second term? That's what I want you to tell me. No. Good. So this is the left hand side. To be compared with what? This is, to this order of accuracy is equal to minus I by 2 gamma dot sigma minus 1 by 4 alpha dot beta, to this order. And you see, this cancels. This would not have cancelled if on the right we had not retained this contribution. So it tells you that you should keep that, because it will match this term. And now see what is gamma. Compare the rest. What is gamma? Half? half alpha cross. So what have we found? If you take two elements of SU2 both close to the identity and ask what is the result of their composition, here it is. Does this ring a bell? Huh? Yeah, they don't commute. That is one thing. But do you recognize having seen a similar thing some time ago? For SO3 in similar axis angle description? Same. So what does it mean? Near the identity, these two groups, SU2 and the earlier SO3, are isomorphic. Their composition rules are identical. So we say they are locally isomorphic. And global, the differences between them are global. So I wanted you to see how the use of the axis angle description leads, in a way, the algebra here is easier than for SO3 because these are 2 by 2 matrices. Pauli matrices are so elementary. For SO3 we had to use 3 by 3 matrices. That's also not complicated, but this is just a shade simpler. So you see the local isomorphism. The two groups look the same near the identity. So in a picturesque way, if you are sitting rather close to the identity, you don't know whether you are sitting in SO3 or you are sitting in SU2. They look exactly the same. Now the next use of this axis angle description will be the following. We saw already yesterday that this group, the manifold of the group is like the unit sphere S3. And so by extension of what we know in 3 dimensions, we just jump to the conclusion it must be simply connected. Every closed loop in this group can be shrunk to 0. Now let me show you this same result in axis angle variables. I'm sorry. I will separate the axis from the angle. This is correct, is it? No factors missing. And what is the range for alpha? Huh? Pi, 2 pi, pi by 2, how much? 2 pi. Okay. All right. So now I will try to be a Raphael again. Let us draw a circle first. Sorry, it will look awful in the video. But anyway, but I won't make that stupid error I made in the last week when I drew similar figure and Simon pointed it out. This is just to get your bearings. I draw this also. All right. So this is the space of parameters 3 vector alpha. This is axis 1, this is axis 2, axis 3. That is alpha 1 is plotted in this direction, alpha 2 here and alpha 3 there. So the radius of this sphere is now 2 pi. Remember in the case of SO3 we needed only a sphere of radius pi. Now in the case of SO3, actually I feel very uneasy to see this rather poor circle. I will try to improve it. Let us see. Not bad. Okay, it's better. In the case of SO3, for comparison, if you remember, the sphere was half this radius. Here is the identity element or the origin in alpha space. And if you are close to the identity, each point in this solid sphere in the interior corresponds to a definite group element, and vice versa. There is no confusion. But the sphere was of radius pi. It ended somewhere here. And when you came to that surface, distance pi from the origin, you had to make a special rule. Every point represents the same element as the diametrically opposite point. So opposite pairs of points were suddenly identified when you reached the distance pi, the surface of the sphere of radius pi. And why was that so? It was because whether you make a 180-degree rotation around axis n or axis minus n, it makes no difference in physical three dimensions. Now, with the case of SU2, again it is true that if you are in the interior of the sphere, away from the surface, distinct points stand for distinct elements in the group. There is no confusion. But what happens when you reach the surface? And remember now, the distance you have to travel to reach the surface is 2 pi, not pi. What is this 2 by 2 matrix? Huh? Identity? Yeah. No? Minus identity. 2 by 2. But this thing is even independent of n. So what does it mean in this picture? What is the identification we have to declare when we reach the surface? Huh? Yeah, it's not just diametrically opposite point. All points on the surface are one and the same group element, not the identity element, but the element minus 1. Now I want you to understand why this makes this group simply connected. That jumping across from from North Pole to South Pole, or as they say from East Pole to West Pole, which we saw could be done in the case of SO3, it is not needed here. Suppose I start from the identity, I go like this, like an ant, and I reach a point on the surface. And now I'll just switch to some other arbitrary point and crawl back to the unit element. I'm not jumping to a diametrically opposite point at some other point. Is this a closed loop or not a closed loop? It is a closed loop. You can do this any number of times, any place on the surface, because they're all one and the same element. So so you agree this is a closed loop, though it doesn't look like it. Can you shrink it to 0? How would you actually shrink it to 0? Why don't you come and do it? You'll also come in the video. How would you just draw some pictures to show how this closed loop can be continuously shrunk to 0? What would you do? I want to give you a hint. In the SO3 case, suppose this was the surface of radius pi. You came here, either you could stay there or jump to the opposite point. If you want to modify that loop in some way, you might shift this. Automatically that would move. Here, is there any such constraint? So how would you shrink this into the trivial loop?
I'll move this here.
Yeah.
And if there is no constraint, I'll move this here.
Into the inside?
No. On the surface.
On the surface.
Such that at some place they meet and there I can then take it to the center.
You don't even have to do that. Even simpler. Keep this as it is. Just lead this by your hand along the surface, go up to there, then plummet down. So because all points on the surface of radius 2 pi are the same group element, that is what, in spite of appearances, makes this a simply connected space.
Such a nice thing. So I just wanted to look at it in one dimension.
One dimension smaller.
So that
Yeah.
becomes
Yeah.
so if you take a half sphere,
Half hemisphere.
hemisphere,
Ah.
the hemispherical shell, not a solid sphere. So this
Okay.
two-dimensional thing.
Okay.
Okay. And then you say that along the ring, you stitch the opposite points together.
Yeah, yeah.
You will find that it's something that you cannot actually do in
Ah.
two dimension.
Yeah, yeah,
But
yeah.
whereas if one says that identify all the points of the thing, you still get a
Yeah, yeah.
uh,
Identify not diametrically opposite,
no,
but all points.
on the
Rim.
on the boundary.
One ring.
Together you get a sphere. So
Yeah.
this is
Yeah.
probably a similar thing.
Yeah, yeah. In one higher dimension.
higher.
One higher dimension. Yeah. Okay. So I think such pictures are illuminating for us if you are studying these things for the first time. If the simple connectedness of SU2 is obvious to you very directly, well and good. But if it is not, you might find such pictures quite useful. Okay, so now I want to use this description, axis angle description, for another purpose, and that is the purpose of describing the conjugacy classes in the group SU2. But it turns out that the convenient way of doing that is to first clarify the proper relationship between SU2 and SO3. What we have appreciated up to now is that they can be described in very similar ways. Every way you describe SO3, SU2 has a companion description with a double the range for the parameters, roughly speaking. Then we have seen near the identity, they look identical. So exactly where do they differ and how can we make that statement precise? That comes by a careful study of the real relationship between these two groups without any approximations or saying we are near the identity, without making any such statements. So this is done in the following way. You define a set M is as the set of all 2 by 2 Hermitian traceless matrices. So now every such matrix can be written as a combination of the unit matrix and the Pauli matrices are a basis for all 2 by 2 matrices, right? There are 4 of them. If I want to write a matrix of this kind in terms of the Pauli matrices, what will it look like? Some? Yeah, what kind of vector? Real 3 vector. For every real 3-dimensional vector, I can construct a matrix belonging to this set M. All right, this is a one-to-one correspondence between physical 3-dimensional space, you can say, and matrices of this type. Now we do the following. You take a matrix from the defining representation of our group and you take an object in this set M and then you conjugate x dot sigma by u. You put u on the left, u inverse on the right. What kind of matrix is u x dot sigma u inverse? It is 2 by 2. Is it Hermitian? Yes, yes. Is it traceless? Yes. So it is one of the elements of this set M. Therefore, it must be of this form for some 3-dimensional real vector x prime. No choice. No? How does x prime depend on x? Is it linear, quadratic, cubic? What is it? Linear. It is linear because there is nothing else here. So x prime must be some linear transformation determined by u acting on x. Now I go back here and ask you, What is the determinant of x dot sigma? Well, so for that purpose, please dictate what is the 2 by 2 matrix explicitly in terms of x1, x2, and x3. Huh? x3, x1 minus I x2. So the hermiticity is made very clear, tracelessness also. What is the determinant of this? Huh? Minus x dot x, the square of the length of x. So now two things are clear. Will this determinant change under this conjugation? Can it change? Because it's u, something u inverse. So the determinant of u, anyway it is 1. So it doesn't change at all. So what does this mean? X is any real 3-dimensional vector. X prime is some 3-dimensional vector obtained from x by some linear 3 by 3 operation. The determinant of this equals the determinant of this. What does it mean? The length of x prime equals the length of x. So what does it show you? For any element u in SU2, L of u is some 3-dimensional orthogonal rotation. It may be proper, it may be improper. At this point we do not know. Next what you do is you do this conjugation once more, and then you will easily convince yourself that the matrices which you get in 3-dimensional space, incidentally these L's have to be real matrices. They will necessarily be real because x prime has real components, x has real components. So even though u is a complex 2 by 2 matrix, the L of u which is produced by this operation is a real 3 by 3 matrix. And doing this conjugation twice and looking at the results, you will find L of u must obey this property. And now we switch on what we have learned, that SU2 is simply connected. Connected is good enough, but simply connected even better. It shows that L of u obviously varies continuously with respect to u. When u is the unit element in SU2, what is the matrix L of u? Unit matrix, 3 by 3 unit matrix. At that point it has determinant +1. We know that L of u preserves the square length of x. So either it is a SO3 rotation or an O3 rotation. It cannot be O3 because SU2 is connected and you can reach any point in SU2 continuously starting from the identity. So the L of u, because it depends continuously on u, it cannot suddenly switch sign for its determinant from +1 to -1. So what have you shown? You have shown there is a well-defined rule which takes you. Now I want to change my notation. Instead of capital L, I will use capital A. Change of notation. So there is a well-defined rule by this procedure which carries you from each element of SU2 to an unambiguous, well-defined element of SO3, which I write as A determined by u, such that that multiplication rule of SU2 is respected. In fact, one can easily write down the explicit expression for the matrix elements of this 3 by 3 matrix. I will just do it for you. The equations are very simple. If you want the explicit matrix element expressions, you just conjugate each one of the 3 Pauli matrices by u, one at a time, and see what happens. And so this get this result, and therefore I have a formula one half trace sigma k u sigma j u inverse, and this has a number. So here is the explicit formula. Take any SU2 matrix, 2 by 2 matrix U, put it into this machinery, and you will get a 3 by 3 matrix A of U. And that will be a 3-dimensional proper rotation, and the mapping from SU2 to SU3 is such that this multiplication law is obeyed. So what do you see? What you have is something we had defined some time ago. We have a homomorphism, a mapping from SU2 to SO3 such that the multiplication law is respected. So this is the Pakka relationship between these two groups as a whole. There is a homomorphism from SU2 to SO3. So the roles are not symmetric. That you must appreciate. It works in this direction. And now I want to say that the various parameterizations which I have described first for SO3 and then for SU2 have been set up so that they match properly. What I mean is now the following. You take, let us say, the axis angle description of SU2 elements. So you give me alpha, I know what SU2 matrix you have in mind. I now put it into this machinery. I should get from here some SO3 rotation. Axis angle for SO3 has been set up so that you get A of alpha of SO3. So it is in this sense that the axis angle description for SO3 and the one for SU2 match perfectly in the sense that the parameters are preserved under the homomorphism. Similarly, take the homogeneous Euler parameter description of SU2. Put it through this machinery. What is the SO3 matrix you get? It is the one which we described long ago with the help of homogeneous Euler parameters. And what else have I to do? I have to look at this and ask, what do I get? I get the Euler angle description of SO3. So it is in this sense that the three parameterizations which I have been describing to you are matching. In the mapping from SU2 to SO3, modulo something which I will just now say, parameter values are preserved. What is the cautionary statement I should make? This is not a one-to-one mapping. You know that when you have a homomorphism, there is something called a kernel. What it measures is the following. For each SU2 element, there is a unique SO3 element. But is it unique in the opposite direction? Suppose I say, I want a particular SO3 matrix to be produced by this rule. Is there a unique starting point or is there some freedom? It depends on how many SU2 elements are mapped into the identity. If you know that, you know for all elements the amount of freedom. That part is called the kernel. So now I ask you, go back there. If I want the vector x prime to be the same as the vector x, that is, I want L of u to be the unit element of SO3, I don't want any change in going from x to x prime. Does u have to be the unit matrix or can it be something else? Minus. Is there any further possibility? Phase factor. Phase factor times unit matrix. But what is the condition on u? What are the conditions on u? U should be unitary and determinant should be plus 1. So there is no more freedom, no other arbitrary, no general continuous phase factor. So the kernel consists of just the two matrices 1 and minus 1. This part is called the Z2 subgroup of SU2. It is a two-element subgroup, and it's an invariant subgroup. And therefore, you see that now you see all pieces of the jigsaw puzzle are in place. Here is the true description of the relationship between these two groups. SU2 has a center. Center means things which commute with everything. It is a two-element center. That is an invariant subgroup, abelian. It is the kernel of this relationship, this homomorphism. When you take the quotient SU2 over Z2, that is exactly SO3. No ifs or buts or no mismatch anywhere. This is a correct, complete statement. Now what happens is the following. We can say now we have a 2-to-1 mapping, 2-to-1 mapping from SU2 to SO3. And in equations, you can see here, look, it is quadratic in U. So the element U of SU3 and the element minus U, which is also in SU2, they both will lead to the same rotation. Yes?
So we have like SU2 by Z2 is SO3. Similarly, we have O3 by Z2 is SO3.
O3
by Z2.
Which is at, oh, parity.
Yeah.
Yeah.
So equal to SO3.
Yeah.
So can we say anything about this relation?
No. O3, it's not even fully connected. Here, SU2 is connected, simply connected. SO3 connected, simply doubly connected. O3 not even connected. So you can't say anything. Okay. So SU2 does not take you anywhere near O3. Improper rotations in 3 dimensions can never arise starting from SU2. At most SO3, only SO3. So this is a precise sense in which we say that SU2 is twice as big as SO3. This is a precise relationship. And now when you, yeah?
Can I add a comment?
Please.
This is Sandeep's thing.
Yeah.
SO3 was a subgroup of
O3. Yeah.
SO3 is not a subgroup of SU2.
Yeah. In any sense. Yeah. Don't think of it at all in that as a subgroup. It is not. Yeah. Very good. I think it's a very important point. So this 2-to-1 relationship is seen in all of these parameterizations. If I start from this lowest one, remember for SU2, theta goes all the way from 0 up to 4 pi. I mean, that was one possible choice. Psi and phi had the same ranges for both groups. So that's a doubling. What it means is that the SU2 element with some set of Euler angles and a different element with theta plus 2 pi, that will be just a negative of this. And it will not show up at the SO3 level. So the range of parameters for SU2 is double the range here. What happens with homogeneous Euler parameters? It's simpler. For SU2, a point A on S3 and a point minus A on S3 are distinct SU2 elements, but they are negatives of one another. And there, that difference is washed out when you go to SO3, which is why when you use homogeneous Euler parameters for SO3, we have to remember that the point A in S3 and minus A are the same element. And here also, for SO3, it is enough to let alpha run in magnitude from 0 up to pi. For SU2, we must go up to 2 pi. And as you allow alpha to go closer and closer to 2 pi, you are going into new regions of the group SU2. But the region from 0 to pi and the region from pi to 2 pi each of them maps into SO3 as a whole. And so pairs of elements in SU2 have common image in SO3. Okay, so all this is more or less clear, but if you are seeing it for the first time, this is useful to picture it in this way. All right, so here we have the homomorphism. And my aim was to bring out the fact that the detailed descriptions of group elements have been set up so that there is a matching of the parameters which we often use. So now we can talk about classes in SU2. This little exercise is very useful. What we can say is the following. You take a general element U and you take the axis angle labeled element in the middle and U inverse. So this is conjugation. So let me write it out. Sorry. Cos alpha by 2 minus I n dot sigma sin alpha by 2 U inverse. All right? First term, no change. The unit matrix remains as a unit matrix, U cancels. Then what happens in the second term? Minus I? Huh? Yeah, and how much is n prime? L of U. And what did L become later in my notation? A. So what should I write here? A of U n dot sigma sine alpha by 2. It's a complete result of conjugation. So what does it tell you? It tells you that conjugation leaves the magnitude of alpha, the amount of rotation roughly speaking, fixed. It just changes the axis exactly as it did in the case of SO3. So with this information, and you can also see that take one axis, every other possible axis can be reached by this formula. Only alpha is unchanged. So now we can make a nice list of all the equivalence classes of the group SU2. Let us see what they look like. They look like this. Each equivalence class is labeled by this angle parameter alpha. For each alpha you have a class. So for alpha equal to 0, what is the equivalence class? What is it made up of? Identity. 1, I shall say 2 by 2. So it's a single element class. Then I look at various group elements in the interior of this solid sphere. So for each such alpha, I have an equivalence class of elements the axis varying over S2. So how many elements in each class? Infinitely many. And S2 worth of elements, as Balachandran would say. Okay, every class has an infinity squared number of elements. And now what is left? Alpha equal to 2 pi. What is this equal to? Minus 1, single element. So these are the equivalence classes of SU2. You can see the dimension change discontinuously. It is not like coset decomposition. Cosets always have the same dimension, but this is different. And it's also true that for any class, one can choose a convenient representative element, and it is this element. Oh, I have the minus sign in the wrong place. I'm sorry. I put it here. This is a convention. So you take the diagonal elements of SU2. Each one of them belongs to a different class. It can be taken as a representative element of the class. So class number alpha, if you want to reconstruct the whole thing, what do? You start with this diagonal matrix and then conjugate it with all SU2 elements. And then you'll pick up everything else in that class. So this is, my equation numbers are going haywire. This is equation 83. I think there is some idea, some hope, some possibility that things may be typed and I may proofread them. Then in that all the equations, everything will be there. So it doesn't matter if I omit some numbers once in a while. This is just to show you we have come so far in this section, 83rd equation. All right. Now, what would you say is a class function in the case of the group SU2? How would you describe a class function? A function on the group which is constant over each equivalence class. How would you describe such a function? How would you write it? Function of alpha, f of alpha. And what would be the range for alpha? Open, closed, half open, half closed, what? What's the range for alpha? Strictly speaking. Huh?
Open from both sides.
Why? Why should I not include this class? Why should I omit this class? Is there any reason? Things are discontinuous, I agree. The classes, they change dramatically at 0 and at 2 pi. But if you want to say you have a function defined over all the classes of SU2, you have to write it in this way. Huh?
But from both ends, the function is just constant.
Beg your pardon?
But on both ends,
The
function is just constant.
How do you mean? This class is made up of 1 point. So it means if I have a class function, I have a function which has a value for each class. So here, this class consists of one group element. The function has some value at the identity. Here it has some value at the matrix -1. Here it has some value over, well, go back to that solid shell picture, radius 2 pi. Where is this sitting in that picture? At the origin, single point. What is this one in this range? It's a shell somewhere in the interior. It has many, many points. Where is this one?
Outer shell, but the
Outer shell. But do you have many points or 1 point? Just 1 point. Okay? So if you say you have a class function, it will be a function defined over that solid sphere of radius 2 pi. But when you reach 2 pi, the function better have the same value at all points. You cannot imagine a function as being a class function and having different values at different points on the surface. In the interior, it is a function only of distance from the identity. Outside, it has to be constant everywhere. All right? Okay. So that is all right. So I think you are getting a good feeling for this group SU2. It is, so we say that SU2 is a double covering of SO3, a twofold covering of SO3. And I will just make some statements now, which I will not go into in any detail even later, but just to give you a qualitative idea, so that if you want, you can read a little more. The idea is just that suppose you started with the group SO3. It is a group. It is no hanky-panky from that point of view. But you have found topologically it is non-trivial. It has double connectivity. It is doubly connected. Then one can ask the question, is there bona fide, a pakka procedure to take a continuous group which is connected but maybe multiply connected, somehow do some surgery, some operation on it, so that you convert it into a simply connected space but preserve the group structure. Can you start with a group which is connected like SO3 but which is not simply connected? Still it is a group. Maintain the group structure but somehow alter the topology to make it simply connected. Is there a way to do this? And if you do this, will you can you do it maintaining the group structure? What will you get at the end? Well, I am not going to give any further discussion of this this idea and this procedure in this course, but it's worth pointing out. There is a way to do this. There is a very well defined, very beautiful way, which is very picturesque also in a way, you know. I will describe it, though I am digressing, but it's worthwhile. There is a way to start with the group SO3 and carry out certain mathematical operations which alter the connectivity. You can't alter the connectivity of SO3. It has multiple double connectivity. You modify it, you massage it and produce out of it a simply connected group. So what is being done? Near the identity you maintain the group structure. Globally you make some major change and you end up with a new group. It cannot be the old group, but you end up with a unique new group. It is completely defined by the following two properties. Near the identity it is isomorphic to SO3. Globally it differs, but in such a way that it has become simply connected. This is a unique procedure. To start with a group which is connected but not simply connected, maintain the group structure near the identity, but globally alter it to become simply connected. That is a unique procedure, and in the case of SO3, it leads uniquely to SU2. Okay? So, I don't write equations, I just give you a verbal description. So, we say SU2, it's a two-fold covering of SO3 that we have seen explicitly. It is the unique simply connected covering group of SO3. It's a unique simply connected covering of SO3. It then has another name. It is called the universal covering group of SO3. Universal means in this context when you convert non-trivial connectivity into simple connectivity. When that is achieved, you say you have gone to the universal covering group. I think I should stop for a moment. I just want to say if you have a high quality, good quality mathematical training, then I think your ideas about these things become much sharper and you have more confidence in the statements and so on. With training like mine, you know, unless one writes down some coordinates and does some explicit 2x2 matrix, one sees it in detail, one is always unsure what is going on. I suffer from this, and my feeling is that most of us who have a physics biased training have this problem, and I can make a global statement, not simply connect, but global statement. Those people who study physics in the continental countries, especially France and Italy, they have a better sophistication in their mathematical training. Those who have studied, like many of my generation in the United States, our mathematical training is not as sophisticated as the continental. The reason partly has been that in the US, physics departments always thought they must teach on by themselves courses in what they call mathematical physics. The general tradition in the United States has not been that a physics graduate student will learn mathematics in the mathematics department. No, we will teach our own brand of mathematics. But I tell you, in Italy and in France you go, the language that the physicists use, the way they feel at ease with mathematical concepts, it is distinctly better than the average the middle America. I don't mean the most gifted people, most people. So some years ago, Simon and I wrote a long paper, 30 pages or something. The whole purpose was to carry out this universal covering group construction. Such laborious detail. Until we did it in gory detail, not for this group but for a non-compact group, until we did it in all detail, 30 pages, we were not satisfied that we had really understood it. And lo and behold, at the end of it, we wrote this in honor of well-known physicist Biedenhahn. When he said it, he said he never knew all this. He was a student of Victor Weisskopf at MIT, trained by one of the very best people in the USA.
But trained in USA.
In USA, in one of the best US institutions. Huh?
Not in France or Italy.
No, in MIT. By the way, Weisskopf was a classmate of Gell-Mann, and as an undergraduate, I think. Because where did Gell-Mann go for his PhD? Chicago, right? Gell-Mann also was Weisskopf's student. They were both students of Weisskopf, if I remember. And they were trained by very good physicists in a very good institution. But and Biedenhahn is world famous for his work in group theory. This thing he did not know. But the only way we could do it was by brute force construction. But if you have so I think you have to change it now. Same boat as me, you have not much hope left. I don't mind saying it. But there are younger people who have many more years to go, and it is possible for them to have a better mental attitude. Partly it depends on how one is taught, you know.
I have one objection to your statement.
Every statement I know you can object. Sorry.
Yourself you said.
Huh?
Yourself you said. If you don't with respect to pure mathematics.
Yeah.
My contention is that
Yeah.
to be creative in sciences, you have to come out of logic.
Come out of?
Logic.
Yeah.
When you
Yeah, I agree.
don't try to, your way of trying to go into the pure mathematician,
Yeah.
you become a logical person, prove good theorems,
Yeah.
etc.
Yeah,
and
yeah.
you can change the accept
Yeah.
that will to get your answer.
Yeah.
Nature is not under your control.
Perfectly
You just
right.
have imagination. That
Yeah.
gets killed.
Yeah.
Once it gets killed, you
Yeah.
cannot have a creative idea coming.
I agree.
The part of creativity
Yeah.
is to put pure mathematics at its place.
I agree. So
I'm
you,
not you. I'm
Yeah.
saying because you are
Yeah.
one of the very creative physicists.
I don't know.
No.
Okay.
You may, for instance,
Yeah.
if he compared
Hmm.
to somebody else.
Hmm.
In fact, if we had lived with him, we would say that he is no better than us. We don't
Who?
know.
Who?
Any of the great ones, if we had
Yeah.
lived with him,
Yeah.
we would probably say, well, that fellow does know much more than me or whatever. That's not the point. One does not have to feel inferior because we could not do it their style.
I will not object to what you are saying, but I will modify it only in this sense that if you want to be a very good quality theoretical physicist, and I hope there are many of you here who have such an aspiration, don't allow the mathematics to become a stumbling block in any sense. If possible, retain your physical intuition, the kind of way of thinking that a physicist needs, which as you say, but don't allow mathematical complexity to hold you back in any way. That is all I am saying. For me it is very difficult. When I was a graduate student, I was taught my mathematics in a particular way, and it was the general US pragmatic approach. Every physics department, even, but however, I must say in places like Princeton and Harvard, very good physics students do go to mathematics department for some of their courses if they need to. In the second rung, I would say, like Michigan or Columbia, I don't know, Rochester certainly, physics students got their mathematics in their own department. They generally did not go to the mathematics department. So if you are able to imbibe their way of thinking about mathematics, you may then be able to exploit it far more easily for physical purposes. That is what I am trying to say. And I feel that physicists, theoretical physicists in France and in Italy, these two I know reasonably well, they are not put off, or they don't feel discomfort in dealing with sophisticated mathematics. They know how to operate and discuss at that level. This is my feeling. In Russia, on the other hand, the old Soviet Union, that was in many ways the best blend. The mathematicians of the old Soviet Union wrote books knowing that it will be read by physicists, and their style of writing, it's, from our point of view, far better than main continent, French books, Italian books in mathematics. Look at Russia, old Soviet books on mathematics, so beautifully written, and all the physicists and engineers learnt from their mathematicians, their world-class mathematicians. But there was always this tradition, we'll write in such a way that everybody should understand. You know, this is in the US, all the well-known textbooks on mathematical physics are by theoretical physicists, all the well-known books. But it was not true in Europe. Courant and Hilbert, Gelfand and Shillov, look at all these books. The European tradition was different. Anyway, that is a digression. So I will take a little extra time today. So I want to describe, one other thing. So this kind of discomfort that I have had, and I once asked Professor Bargman in Princeton, Professor Bargman, can you tell me what is it, this differential form, can you give me some idea what are differential forms? He said, antisymmetric tensors. That was his answer. It's a real down-to-earth numerical way of looking at it. So he was also from that old generation. But if you look at people like Abhay Ashtekar, who is a physicist, but he has no difficulty dealing with sophisticated mathematics, not to speak of other great giants and so on. Okay, so let me make this my message, that you try to get that spirit of pure mathematics, tailor it to your needs, don't sacrifice your physical intuition if you have it, and in that way you can make the best of both worlds. So now let us look at this idea of integrating a function defined on the group SU2, and it's a, let's say it's a real function or a complex function, or it can be something belonging to any linear space. It can be in some vector space. How do you define the concept of integrating it over SU2? So here I am going to do this minor surgery. We want to set up some expression of this kind, which is the integral of our function over the group. U is a group element, and that's the argument of f. Values of f may be real numbers, complex numbers. Du is symbolically a volume element. And we want certain invariance properties, whether you integrate the function f of u or the f of u inverse, or translate it from the left or translate it from the right, we would like all these things to be the same. Now, by the way, it is true that for compact groups, for finite groups, trivial, we have defined it. For compact continuous groups, there is a way of defining integration with all these invariance properties. For non-compact groups, it is not guaranteed. One may not have a single notion of an integral which has all these invariance properties. I do not know this subject very well. I don't know. There are some conditions on the group which will guarantee that an integral which is left translation invariant will also be right translation invariant. So just making a suggestion to you, go and ask one of your mathematics fellow students, if not faculty, what are the continuous groups for which such invariant integration is possible? You may learn something. I don't know the full answer to this question. So it is possible to set up such an integration procedure for SU2 with the added condition of normalization. If the function is constant and has the value 1, we would like this integral to be 1. That is possible because it's a compact group. For non-compact groups, that normalization is not possible. So I will just let you see the forms of this integration in the 3 parameterizations. I'm sorry, I'm using this parameterization all the time. This girl would be really very unhappy. This is how it looks like for axis angle variables. And now I want you to appreciate something very pretty. Near the identity, what does this thing look like? It's a constant. So roughly speaking, close to the identity, a small region of the sphere is a reasonable amount of group stuff. As you reach the boundary, alpha equal to 2 pi, this function goes to 0. So you may think that in that pictorial representation, I will look at a thin spherical shell near alpha equal to 2 pi. It looks so big, it has very little volume, right? Because cosine alpha approaches 1 as alpha goes to 2 pi. So this anyway, the reason why this factor is present is because we have demanded all these invariance properties. And so there is a unique answer, and it is also normalized. So this was the axis angle description. I am giving you the results. I am not showing you the derivations. I hope someday you will try to find the derivation. So this is the homogeneous Euler parameter description. And now we don't make any statement that f should be an even function of the argument. Different points on S3 are distinct group elements. And now lastly, we must show it in Euler angle form. And d theta, d phi, so here it is in all gory detail. I think you can easily derive these things. Try first to get this, because geometrically it is very easy to picture. Once you get this, you can transform it into the other types. So this is the concept of invariant integration over the group SU2. Using this, we can define what we mean by the space of square integrable functions on the group. What will it be? It will be a set of all, space of all complex valued functions on the SU2 group with this condition that the invariant integral over the group of mod fu squared, that should be finite. So if a function on the group is such that this is finite, then we have a square integrable function. If this integral diverges, that f of u is not to be included in this space. That is understood. So in what kind of quantum mechanical situation might one think of these as a physically relevant wave functions? If there was a physical system whose configuration space is SU2, if there were such a system, then we would say that this is the space on which we would write a Schrodinger equation and so on and so forth. Okay. Suppose you have a class function that is a function which does not depend on all components of the 3 vector alpha but only on the magnitude. For class functions, this expression simplifies, and I would like to have an expression for that. For class functions, well, this is, as you say, abuse of notation. Notation is meant to be abused. So I just denote by the same letter f a function on the group. I assume it is a class function, which means it does not depend on the direction of the vector A but only on the magnitude, and here is the expression for the integral over the group of a class function. This is important for characters. Okay. So if you don't mind, I will take 5 minutes or 7 minutes more, just get started on the next topic and then stop. So in the case of SO3, we have put down some of the important properties of its representations. So I will do the same thing here. And you will see some new features appearing, which will put everything into nice perspective. I want to list some of the important properties of SU2 representations. So when I finish writing this table, you must then later tonight compare the statements here with the corresponding set of statements for SO3 and appreciate what are the things which are similar, what are the things which are different. There will be some important differences. So 1, every representation may be assumed without loss of generality to be unitary. This is so because we have a compact group. So we need only find all unitary irreducible representations to have complete control over the representation theory of this group. Because if you have all the irreducible ones, you take direct sum and you get all representations. Now comes the next statement, which is new. Nothing like this was there for the SO3 case. Big relationship between these two groups. Every unitary representation of SO3 or every irreducible unitary representation of SO3 is, as it stands, a unitary representation or UIR of SU2 also. How do you show this? Well, I'll show you. You fill out the details later. Statement is given some representation of SO3. That is given. I want to create from this a representation of SU2. What will I do? I want to exploit the relationship between the two groups. What is the relationship I have? For every SU2 element, I have a unique SO3 element. But pairs of SU2 elements have common images. And this mapping is such that it respects composition. So this is given. This I would like to construct. How shall I, in a natural way, construct script D for a SU2 element in terms of capital D for an SO3 element. What equation shall I write? This is something to be invented in terms of something already given to you. What shall I write on the right hand side? D of A of U. D of A of U. Very good. Here I use the homomorphic image from SU2 to SO3. Here I use a given representation of SO3. I claim that this is a representation of SU2. How do you prove it? Script D of U prime, script D of U. What is it equal to? D of A of U prime, D of A of U. I am saying it in words. But it's an SO3 representation. So it is D, capital D of A of U prime, A of U. But what is that? By the homomorphism, it is A of U prime U, which is therefore script D of U prime U. So it's so beautiful, it all matches perfectly. Every representation or irreducible representation of SO3 is a representation of SU2. However, it will not be faithful. What does that mean? What do we mean by saying it is not faithful? Huh? No. Isomorphism is the relationship between two groups.
More than one element of a group can be mapped to
Huh?
more than one element of SU2 will be mapped to
Will be represented in the same way. Distinct group elements are not distinguished by the representation. Why is this happening? Because basically you have only an SO3 element representation. So elements of SU2 which have the same image in SO3, this construction cannot tell them apart. So the statement is, indeed every representation of the smaller group is also a representation of the bigger group. SU2 is bigger, SO3 is smaller. But it suffers. It is not a faithful representation. So one can also make the following statement. I will write part of the sentence. Faithful representations, we have not yet constructed them, we have not yet described them, but we are going to. Suppose you had somehow a faithful representation of SU2, all right, which means it was a representation, script D, in which distinct elements of SU2 are represented in different ways. What statement can be made about such a representation of SU2? It's a negative statement, but what is the statement? Yeah. I am making some of these statements in some detail because sometimes there is a little bit of misunderstanding.
So we can say that it's an isomorphism in the sense that the representations are homomorphisms, from G to GL3 when these the representations.
Yeah. Okay.
If it is faithful, it's one-to-one, so in that
Yeah,
sense it is isomorphism.
Okay, correct. All right. Very good. I think you were still going on that track. So maybe you didn't follow the rest of what I was saying. You were thinking about that. Correct. What you said is correct. Okay. Third property, there is one unitary irreducible representation in every dimension, and traditionally it is written as 2j plus 1, where small j is allowed to take these values. For integer j, these are the odd dimensional UIRs of SO3. So they appear again in this new list of SU2 representations, but as non-faithful representations. For half odd integral j, that is half, 3/2, 5/2 and so on, that is they are even dimensions, they are faithful SU2 representations, but not SO3 representations. That you have to be very clear. What is the defining representation? Is the one for j equal to half. So the dimension 2j plus 1 is 2. So the group SU2 is unique among all continuous groups in the fact, continuous compact groups, in the fact that in every dimension there is a representation. No other continuous Lie group, compact group has this property. If you look at SO3, it has no irreducible representation of dimension 2 or 4 or odd dimensions like that. It has only in specific dimensions. And moreover, it has a very special property. In every dimension, there is only one irreducible representation apart from equivalence. Apart from equivalence. Even that fails for other groups. Then fourth property, and maybe I may stop after that. Fourth property. I will introduce this notation. D superscript j will represent the jth irreducible representation. Its complex conjugate for every j is equivalent to the original itself. However, for j equal to integers, they can be made real, and for j equal to half, 3/2, etc., they cannot be made real. There is no way of choosing a basis in the representation space such that the matrices of the representation all become real. That's impossible, even though the representation is, in the sense of equivalence, the same as its complex conjugate, but they cannot be brought to real form. Okay, so I think I will stop at this point.